Perhaps a radio signal detected from Proxima Centauri indicates that it was received in a very narrow band of frequencies from the habitable zone, specifically from a transmitter on the surface of Proxima b. This is the planet that orbits Proxima Centauri. I calculated that the frequency would drift. Imagine a world orbiting the star closest to our solar system, where liquid water might flow, yet relentless radiation could strip it bare. This is Proxima b, a planet that challenges everything we know about habitability. The discovery of Proxima b, a rocky planet orbiting Proxima Centauri, is a major milestone in the search for habitable worlds. What makes Proxima b so intriguing is its location in the habitable zone of its host star, where liquid water could potentially exist. However, habitability isn't just about location. The planet's ability to support life depends heavily on the intense radiation it receives, from X-rays to ultraviolet and infrared light. Understanding this radiation is critical for assessing whether Proxima b can retain an atmosphere, sustain surface water, or even host life. This video has two main goals. First, to explore the radiation environment of Proxima Centauri and quantify what reaches Proxima b. Second, to refine our understanding of Proxima Centauri itself, its mass, size, temperature, and brightness, as these factors shape the planet's potential for habitability. By combining observations across wavelengths, from X-rays to infrared, this research provides a detailed look at the star's emissions and their impact on Proxima b. Proxima Centauri, located just 4.24 light-years away, is the closest star to our Sun. As a red dwarf, M5.5 spectral type, it's much smaller, cooler, and dimmer than the Sun, with only 12% of the Sun's mass and 15% of its radius. Proxima Centauri's surface temperature of about 2,800 K is far lower than the Sun's 5,780 K, shifting its light output toward red and infrared wavelengths. Despite its dimness, Proxima Centauri's proximity makes it ideal for detailed study. Proxima b, the star's closest known planet, orbits at just 0.485 Australian dollars, closer than Mercury's orbit around the Sun. Yet, because Proxima Centauri is so faint, this distance places the planet in the habitable zone. Proxima b receives about 877 W/m superscript 2 of stellar energy, roughly 64% of what Earth gets from the Sun. However, Proxima Centauri's intense activity, marked by frequent flares and strong stellar winds, raises critical questions about the planet's ability to retain an atmosphere and sustain life. Mapping Proxima Centauri's emission spectrum, the study of Proxima Centauri's spectral energy distribution, is crucial for understanding the potential habitability of Proxima b, the exoplanet orbiting this red dwarf star. Proxima Centauri is known for its variability, particularly in the form of flares that significantly increase the levels of high-energy radiation such as X-rays and extreme ultraviolet, XUV, radiation. These stellar flares are much more frequent and intense than those of our Sun, and they can have substantial impacts on the atmosphere of Proxima b. Proxima b's close orbit around its star within the habitable zone exposes it to a considerable amount of radiation. While the star's output is much lower than that of the Sun in terms of visible light, its heightened emission in the XUV spectrum has important implications for atmospheric chemistry. The high-energy radiation can break apart molecules in the atmosphere, leading to the loss of lighter elements, such as hydrogen, over time. This could result in atmospheric erosion, particularly if Proxima b lacks a strong magnetic field or a protective thick atmosphere. The radiation intensity, however, isn't just a threat. In combination with the thermal radiation in the infrared, the energy input from Proxima Centauri also has the potential to shape the planet's climate. Infrared radiation from the star warms the planet's surface and atmosphere, influencing the greenhouse effect. In turn, this affects the planet's ability to retain heat, regulate temperatures, and maintain a stable climate for potential life forms. The study's integration of data from multiple instruments helps build a more comprehensive picture of the radiation environment around Proxima b. For instance, by analyzing the star's X-ray and UV flux in detail, scientists can estimate the amount of stellar energy available for atmospheric heating and determine the likelihood of atmospheric stripping. Similarly, Observations in the infrared spectrum allow researchers to model how Proxima b might retain heat, especially in the face of such intense radiation. Ultimately, these combined observations inform our understanding of how Proxima b's atmosphere might behave in response to its host star's radiation. The planet's potential to sustain liquid water or harbor life is significantly influenced by these radiation interactions. Although the high XUV radiation levels present challenges, there could be regions on Proxima b, perhaps in its twilight zone or deeper in its atmosphere, where conditions are more stable and potentially habitable. However, the balance between radiation-driven atmospheric loss and thermal retention will likely play a central role in determining whether Proxima b could sustain life as we know it. The evolution of Proxima Centauri's radiation is essential to explore Proxima b's potential for habitability. It's crucial to understand both the stellar environment it resides in and the planet's atmospheric evolution. Proxima Centauri, a red dwarf star, is much smaller and cooler than our Sun, but it is also highly active in terms of X-ray and ultraviolet (XUV) radiation. This radiation plays a key role in the development and retention of a planet's atmosphere, particularly in the early stages of its formation. Red dwarfs like Proxima Centauri can be very volatile, emitting intense flares and XUV radiation early in their lifetimes. This period of activity is often referred to as the pre-main sequence phase, and it can last for hundreds of millions to a few billion years. During this time, the intensity of XUV radiation can be many times greater than what the planet would experience today. If Proxima b was exposed to these early bursts of high-energy radiation, the planet's primordial atmosphere, if it had one, could have been stripped away, making the planet less likely to retain water or life-sustaining gases. However, after this initial active phase, red dwarfs like Proxima Centauri typically settle into a quieter phase where their radiation output stabilizes or decreases significantly over time. This creates a second phase in the planet's history where the possibility for atmospheric recovery may emerge. If Proxima b experienced volcanic outgassing, where gases like water vapor, carbon dioxide, and nitrogen are released from the planet's interior, this could have helped build up a secondary atmosphere. Alternatively, impacts from comets and asteroids, which could have carried volatile compounds, might have contributed to the formation of a new atmosphere. In addition to the loss of its atmosphere, Proxima b could also face significant challenges due to its proximity to its parent star. Because Proxima Centauri is a red dwarf, Proxima b is likely tidally locked, meaning one side of the planet always faces the star, while the other side remains in perpetual darkness. This could result in extreme temperature gradients, with scorching heat on the star-facing side and freezing cold on the opposite side, potentially complicating the prospects for life as we know it. Moreover, understanding the timing of Proxima Centauri's activity, specifically the transition from an active to a quieter phase, is crucial for determining whether Proxima b's atmosphere could have had enough time to stabilize. If the high XUV radiation persisted for too long, it might have prevented the development of a thick, stable atmosphere altogether. Thus, while Proxima b remains one of the most intriguing exoplanets in the search for habitable worlds, its long-term habitability depends on a delicate balance of factors: the nature of its star's radiation history, the ability of the planet to develop a protective atmosphere, and the environmental conditions that may have allowed for the emergence of life. Future missions to observe Proxima Centauri and Proxima b, such as the James Webb Space Telescope, will be key to determining whether the planet's atmosphere, if it exists, could support life. Evidence of warm dust in the system, such as the discovery of excess infrared radiation from Proxima Centauri, is indeed intriguing and opens up several avenues for further exploration. The 20% increase in infrared emission suggests that there is an additional source of heat in the system, likely due to warm dust particles. This dust is probably heated by the star's radiation, and its presence is unusual since dust in the interstellar medium generally cools and dissipates over time. The fact that it is still present around Proxima Centauri hints at ongoing processes, such as planetesimal collisions or the presence of a debris disk, which are relatively common in young planetary systems but rare in older ones. The warm dust could have significant implications for Proxima b, the exoplanet that orbits within the habitable zone of the star. If the dust is scattered and absorbed by stellar radiation, it might change the thermal balance of the planet's environment. For example, it could potentially block some of the incoming stellar radiation, affecting Proxima B's climate and surface temperature. Understanding how this dust interacts with the planet's atmosphere could be key to predicting its habitability, especially when combined with data about the planet's atmosphere composition and magnetic field. Moreover, the presence of this dust raises important questions about the system's architecture. Proxima Centauri's dust may not be uniform but could instead be influenced by the gravitational forces of hidden or yet-to-be-discovered planets. These planets could be in elliptical orbits or interacting with one another in ways that disturb the distribution of dust and debris. It's possible that additional smaller planets might exist in this system, perhaps on the fringes of detection, whose interactions with the debris disk could be shaping its current state. Some researchers believe that this infrared anomaly could be indicative of planetary formation processes still taking place around Proxima Centauri. If this is the case, the system may be in a transitional phase where new planets are forming, or remnants of planetesimal collisions could be polluting the region with dust. This dust could also be remnants of a larger planetesimal disk that once existed and was disrupted by gravitational forces from larger planets or stars. In order to better understand the system, future studies will likely focus on a detailed analysis of the dust distribution. Observing the motion of dust particles could shed light on the location and characteristics of potential planets in the system. Additionally, astronomers may look for more subtle signs of hidden planets, such as gravitational microlensing or periodic perturbations in the star's movement. The dust itself may also be studied through direct imaging techniques, which could help uncover more information about the size, composition, and density of the dust, as well as any possible planetary bodies influencing its distribution. The interaction between dust, debris disks, and potential planetary formation in the Proxima Centauri system is a topic that could reveal much about the evolution of star systems, planetary environments, and the conditions for life. It provides a valuable opportunity to learn about a nearby stellar system that may share some similarities with our own. Proxima b, orbiting Proxima Centauri, is one of the most intriguing exoplanets discovered due to its location in the habitable zone, HC, of its host star, where liquid water could potentially exist. This makes it an exciting target for astrobiology and the search for extraterrestrial life. However, its habitability is far from assured due to various factors that could complicate the existence of life. Proxima Centauri is a red dwarf star, much cooler and smaller than the Sun, but it is also highly active, emitting intense X-ray and ultraviolet (XUV) radiation. During periods of high stellar activity, Proxima b could be subjected to harmful levels of radiation. Such radiation could strip away the planet's atmosphere, particularly if it is thin or already fragile. The loss of atmosphere would render Proxima b inhospitable, as a breathable atmosphere is a key ingredient for life as we know it. A strong magnetic field could potentially shield Proxima b from some of this radiation, much like Earth's magnetic field protects us from the Sun's solar wind. However, whether Proxima b has such a magnetic field is still unclear. If it does not have a magnetic shield, the planet would be more vulnerable to atmospheric loss, especially over extended periods. Proxima Centauri's light is dominated by the red and near-infrared part of the spectrum, which affects the potential for photosynthesis on Proxima b. While photosynthesis on Earth relies on visible light, organisms on Proxima b, if they exist, might rely on near-infrared light for energy. This could result in life forms that are quite different from those on Earth, with photosynthetic pigments that absorb infrared light rather than visible light. The spectrum of light received by Proxima b would also affect its climate. The balance between infrared and visible light influences the planet's surface temperature and atmospheric dynamics. It could lead to unique atmospheric behavior, potentially altering cloud formations, convection patterns, and heat distribution across the planet's surface. Such differences could make Proxima b's climate quite distinct from that of Earth, potentially creating an environment conducive to life, but also posing challenges for our current understanding of habitability. The geological history of Proxima b is another factor that might influence its habitability. Like Earth, Proxima b could have undergone significant volcanic activity, which could release essential gases like water vapor, carbon dioxide, and nitrogen into the atmosphere. These gases could play a role in regulating the planet's climate and creating a stable environment for life to thrive. However, if Proxima b lost its initial atmosphere early on, perhaps due to the intense radiation from its star, it would need to rely on secondary processes like volcanic outgassing or cometary impacts to replenish its atmosphere and ensure long-term habitability. Studies of Proxima b's geology and atmosphere are still in their early stages, and further research is required to understand the planet's evolution and its ability to support life. Advanced models of the planet's internal structure, volcanic activity, and atmospheric composition are necessary to gain a clearer picture of its potential to harbor life. Another factor to consider is that Proxima b is likely tidally locked, meaning that one side of the planet always faces its star, while the other side remains in perpetual darkness. This could create extreme temperature differences between the day and night sides of the planet, leading to unusual weather patterns and potentially even the development of unique ecosystems. The tidally locked nature of the planet would also mean that it could have a permanent habitable zone near the twilight line, where temperatures might be more stable. Though whether this zone would be suitable for life depends on many other factors, including atmospheric circulation. While Proxima b shows promise due to its location in the habitable zone, its true potential to support life remains uncertain. The combination of high radiation levels, the effects of its star's spectrum on its climate, and the possible absence of a protective magnetic field or stable atmosphere makes Proxima b a challenging candidate for life. However, ongoing observations and future missions may provide more data on the planet's atmospheric composition, radiation levels, and geological activity, helping scientists better assess its habitability. In summary, while Proxima b's position in the habitable zone makes it a fascinating target in the search for life, numerous factors, ranging from its stellar radiation environment to the possibility of tidal locking and its geological history, mean that its habitability is far from guaranteed. The next steps in studying Proxima b will likely involve a combination of direct observations, such as the study of its atmosphere, and advanced modeling of its climate and geological activity. These efforts will be crucial in determining whether Proxima b truly holds the potential for life beyond Earth. The study of Proxima Centauri's radiation environment and its impact on Proxima b offers a deeper understanding of habitability around red dwarfs. While intense X-UV radiation poses challenges, Proxima b's position in the habitable zone and potential for atmospheric regeneration leave room for hope. The discovery of warm dust adds complexity, hinting at ongoing activity within the system. Future observations, including those from next-generation telescopes like the James Webb Space Telescope, will be crucial for studying Proxima b's atmosphere and searching for signs of life. By combining detailed models with new data, we move closer to answering a profound question: could Proxima b host life, or are we truly alone in the universe?